Imagine you're a race engineer at the pit wall. Your driver is flying around Silverstone at over 300 kilometers per hour, and every second your screen is flooded with live data, speed, throttle, braking, RPM, and gears. You use that data to make the split-second decisions. Call the driver in for a pit stop, push harder, or save the tires. But what if someone tampered with the data without you knowing? Hi, my name is Gabriela Jennifer Sandy, and today I will be telling you and discussing about this problem in a study that addresses this of Merkle tree-based integrity verification for F1 telemetry data. So, the problem is Formula One telemetry is streamed wirelessly from the car to the pit wall in real time. And like any wireless transmission, it's vulnerable. An attacker could intercept the signal and quietly change the value. Like, let's say, making the speed lower than it actually is, or your engineers would have no idea that it is done. There is currently no widely studied cryptographic mechanism specifically designed to catch this kind of tampering in the F1 telemetry. So this study proposes one. So the solution is something called the Merkle tree, a data structure that works like a fingerprint for your entire dataset. Here's how it works in simple terms. Each telemetry data point one row of speed throttle, brake, RPM, gear, and also DRS. They get the converted into a unique code called a hash using SHA-256, a cryptographic algorithm. Think of it like a seal of an envelope. If like anything inside changes, the seal breaks. These individual hashes are then paired up and combined again and again until we get one single hash at the top called the Merkle root. This root is like a fingerprint of the entire lab telemetry. If one tiny value anywhere in the dataset changes, the root changes. So, to test this, the real telemetry data from Lewis Hamilton's fastest lap on the qualifying lap at the 2023 British Grand Prix was used. It was 1,004 data points across the full lap, and two experiments were run. One of them is the speed value that was secretly changed to 999 kilometers per hour. And then the Merkle root immediately changed the flagging and data as the compromise, as the tampering is detected. The second one is the man in the middle attack that was simulated, where an attacker intercepts the data mid transmission using something called a Merkle proof, a small chain of just hashes. The system can verify any single data point is authentic without rechecking all 104 points from scratch. That's fast, efficient, and secure. So what does this mean? It means that the Merkle theories offer a lightweight and cryptographically sound way to protect the F1 telemetry data from tampering and interception without slowing anything down. The entire tree for a full lap is built in milliseconds, and any compromise is caught immediately. Future work will look like at making this work in real time during live streaming and adding digital signatures so the data source itself can be authenticated. Because in Formula One, data isn't just numbers, it's strategy, it's safety, and it should be trusted. Here is one of the qualifying laps that I mentioned before, which is the 2023 British Grand Prix.
Just done the fastest Middlesex, but his first sector, which was fastest initially, that's already been beaten by several others. He's right, he spins. Lewis Hamilton spins off. Now, can he get it out of the gravel? He knows what he's doing. He's gonna get out, I think, and get back onto the track. Well,
here we can see that a millisecond of the speed is very important
Stand
to
out
all the
with
drivers.
the new Google AI Professional Certificate.
Now, I'm gonna run a demo of what of the code that I've done in my Jupyter notebook. You can see here that I've already installed the Fast API pandas of the Fast F1. database. And here we can see that this is how I run the data that I use, which is the driver is Lewis Hamilton, and all I need is the lap time, and the data that I'm getting is the time, speed, throttle, brake, RPM, the gear, DRS of the Silverstone qualifying in the 2023 era. So after I got this data, I will run this series of code, which then will give me the total leaf of nodes, the sample leaf hash, the Merkle root, and also a tempering simulation that I did here. We can see here that after the tempering simulated, we can see that the tempered root is different from the original root. Now, the next code is to see what is the diagram of the Hamilton's fastest lap telemetry. Here we can see the speed, the throttle, the brake, and also the other visualization. In summary, this is the Merkle root, and this one is the tempered root. Next is the Merkle tree structure, where we can see here this is the near leaf level, and this one in the blue one is the intermediate nodes. Lastly, we can see that this is the hash algorithm comparison, where we can see using different SHA can result in quite different hashes. And this is the average time comparison, the throughput comparison, and the digest size comparison. From this thing, we can see that the Merkle root can detect if there is a tempered in the data itself. So that is all for me, and thank you so much, and I hope this is very helpful for you.